This is tutorial 25. We work on examples about pipe losses. In the exam, there must be at least one question about pipe losses, so I deliberately make this tutorial. Before we start working, let's do some revision about losses first. In the last two tutorials, we covered this big part of concepts about pipe losses. But to do problems involving pipe losses, we have to apply the energy equation to relate the losses with the interested quantities, such as pressure drop and flow rate. However, we shall note that whether the flow is laminar or turbulent in advance. Not only are the friction factor different, but the kinetic energy coefficients are also different for the two types of flows. So, we shall always calculate the Reynolds number first if the velocity is available. Otherwise, we make an assumption and verify that later when we get the velocity. Let's use what I have just said in this problem. At the beginning, we know nothing about the velocity. It appears in the figure that the water is moving fast enough, so we blindly guess the flow is turbulent. Here we label points 1 and 2, and we set the datum here. We are ready to write down the mechanical energy equation. The alpha disappeared because we assume that the flow is turbulent. We know the pressure at point 1, and point 2 is exposed to the atmosphere. Point 1 is in the reservoir, so its velocity can be taken as 0. And we are ready to substitute in the values. And then we can use our knowledge about pipe losses. The energy loss is equal to the major loss plus the minor loss. But the V here is the velocity inside the pipe here, which is not V2. To avoid confusion, we write this V as Vp, P for pipe, and then we write velocity as 2 as VO, O for outlet. And if we combine the equation in the previous slide, we get this equation. To get rid of one of the unknown, we shall apply the continuity equation. And we can substitute in this result into our previous equation. So that we can solve for VO. So that we can find the Reynolds number. The V here is 3P. So, our energy equation is valid. And then we can find the flow rate. And we are done with this example. Let's do an integrated problem that requires integration. We want to know about the velocity for this tank problem, but it is not simply square root 2gh. We cannot use Bernoulli equation 2 since there are pipe losses. Let's label point 1 and point 2, and we also let this varying height as h. Then we are ready to write down the energy equation. Both points 1 and 2 are exposed to atmosphere, and both points 1 and 2 are in the reservoir, so they have negligible velocity, and we have just let Z1 minus Z2 as h. But only the major loss is considered in this problem, and it is given in the question that the flow is laminar, so F is 64 divided by Reynolds number, And then we set these two expressions for energy losses to be equal, and we solve for the velocity. And this relation is much more uglier than square root 2gh. But we can let this constant as c. Actually, we know this constant c. Although we can see that this velocity is varying, we know that the flow is always laminar. Since the Reynolds number is directly proportional to the velocity, the maximum of the Reynolds number it can get is the Reynolds number in the beginning. And we plug in the values. Which is well below the limiting value for laminar flow. We let the diameter of the tank to be d, and the diameter for the pipe to be small d. The difference in the volumes in the two tanks is going to be and then, if Q is the flow rate in the pipe, for each unit of volume transfers through the pipe, 1 unit is taken from tank A and 1 unit is given to B. Hence, the rate of decrease in the difference in the volume is the twice of the flow rate. We shall now apply the chain rule. And note that Q is in fact so this cancels out, and V is just CH. This is a separable differential equation, since if we throw things around, and the left hand side is a purely function of H, and right hand side is just a function of T. So we perform definite integral on both sides. At T equals 0, H equals 0.6, and at any instant of time, we already let the height to be H. And we let this constant as A. And we make a change of subject. And the A here is the time constant. It has same unit as time, and we find that to be and this expression together with the A is our final answer. For this problem, there are two sections that has different flow conditions. Let's label this section as A and this section as B. In particular, the flow rate, hence the velocity as the second half of the pipe, that is pipe B, is half of that in the pipe A. So, we shall separately consider each section. Let's see how we can do this. The flow rate is provided to us so that we can find the velocity from the flow rate and calculate the Reynolds number. And we can find the Reynolds number. And since the Reynolds number is directly proportional to the velocity, and now we label this as point 1 and 2 has already been labeled. So we apply the energy equation from point 1 to point 2. We drop the alpha because the flow is turbulent in both pipe A and pipe B. Point 1 is exposed to atmosphere, and we know the pressure at point 2. Point 1 is in the reservoir, and we are ready to substitute in the values. Since the difference in the level is 3H and 1.8. The total energy loss from 1 to 2 is given by the loss in A and the loss in B. And the loss in A can be written as, and same for B. So there are 4 terms to compute, and that is quite time consuming. First, we find the major loss. We are going to use the equation MECH friction factor. For pipe A, the equation is given by and our pipe is smooth. So, for pipe A, and for pipe B, and we verify these two numbers by using the Moody chart. For pipe A, from the graph, that is quite near to our result obtained from the formula. And for pipe B, and that is around here, and that is also quite near to our result. Both values checks, and we compute the major losses for both pipes. And for pipe B, let's also find the minor losses. If you go back to the previous slides, you see that the problem has a sharp inlet between the tank and the pipe A. And the question says there are 15 elbows in pipe A. So the loss coefficient is 5 for pipe A. And for pipe B, there is only a T there. So we are ready to compute the minor losses. From this previous equation, we have the previous example is about flow in series. Now here is an exercise about parallel flow network. So please read the hints I have given here. If you understand that, this problem shall be fairly easy compared to the last example. Our next example is a famous problem about pipe flows. If you Google it online, people write programs for solving such problems. Now, the friction factors are provided to us so that things are easier. But I still think that this problem is too hard to be on the final. Anyway, let's treat this as an exercise. Let's label tanks A, B, C and pipes 1, 2, 3. What is so troublesome about the free reservoir problem is that we don't know the flow direction at tank A. At tank B, of course water is flowing out, since tank B has the highest elevation, and water is flowing into tank C since it has lowest elevation. But for tank A, water can flow out of tank A into tank C, or water can flow from tank B into tank A. So, there are two possibilities. Or, we first assume that this is true, so that we can apply energy equation between point A and point C. Here we also assume that the flow is turbulent, but both point A and point C are exposed to atmosphere, and both point A and point C are in the reservoir, and the elevation between point A and point C is 20 meters. So, and here the minor loss is neglected, so the energy loss is the superposition of the energy loss in pipe 1 and the energy loss in pipe 3. And we are ready to substitute in the values. We solve 3.1 as an expression of 3.3. And similarly, we can apply the energy equation and the concept of pipe losses between point B and point C. I will skip some steps here, hope you understand. From the energy equation, and for major losses in pipe 2 and 3, and this is our second equation. Now, we have 3 unknowns, but we have only 2 equations, so we shall have 1 equation left, and that is the continuity equation. If we apply the continuity equation at this point, so these are tanks A, B, C, and pipe 1, 2, 3, and both A and B are getting into this point, and only tank C is receiving all the things from A and B. So we can write down the continuity equation as, and again, this is in and this is out. So we have, where A is directly proportional to the diameter. And we delete the 0.08. This is our equation 3. But then, we can show that if 1, 2 are satisfied, then equation 3 cannot be satisfied. Consider equation 1. This thing in a square root cannot be smaller than 0, so that we can write down and from equation 2, we can write down a similar expression, and that requires that, and these 2 equations must be satisfied simultaneously. We conclude that, and this information is coming from equation 1. So we haven't used equation 2, and we plug this into equation 2, we get and finally, we also plug this result into this equation. And when 3 is 1.981, 3.1 is 0. But we have just shown in equation 2 that 3.2 must be greater than 5. Now we have shown that from equation 3, 3.2 is smaller than 1.26, so the whole thing is just impossible. So we have made a totally wrong assumption, and this one is in fact the correct flow direction. That is, water is flowing out from tank B to both tank A and tank C. So we have to go backward. Luckily, we still have flow from tank B to tank C. Let's change 3.3 to the subject. And this is our new equation. And similarly, for flow from tank B to tank A, we can write down the energy equation and the equation for the major loss. And you shall eventually obtain that the energy loss involved is and also we shall write a new continuity equation. It is now from tank B to tanks A and C. And these two equations can be combined to give a correct equation 4. Now we solve these three equations obtained from the previous slide. Indeed, that does not require Wolfram alpha. We can solve by hand. First, we substitute this into this and this into this. In short, let's write 3, 2 as 3, and we bring one of the square root to the right hand side. And then we can square both sides. And we shall bring all the things to one side and leave the square root on one side. If we square both sides again, we obtain and we get a nice and short quadratic equation. Solving that, and we can plug in V2 into this formula. So that we can compute the flow rate. And similarly for tanks B and C. And these are our answers. And if we compare our answer to the Wolfram's answer, it's just a little bit different due to the rounding errors. So let me copy the first slide here as a roundup. Today, we do 4 big examples to illustrate how to use these concepts of pipe losses. This is the end of this video and thanks for watching. Feel free to ask us any question and give us any feedback in the comments.